Hello and welcome to week 6, lecture 3. We're going to talk about torque. This comes from chapter 9-1. This week we've learned about the variables of rotational motion, one of which is angular acceleration. And earlier on in the quarter, we learned that force causes acceleration. But what about angular acceleration? What causes that? So let's take a look at this situation. We have a door. And then we are applying these different forces to it to try and get it to open. All of the vectors are the same size, but they either act at different points on the door or they act in different directions. So I want you to pause a second before continuing this and think about which forces would be most effective in opening the door. Maybe even go try it on a door right now. Push near the hinges to simulate force 4. And then push all the way at the end at these different angles. Which one of those works best for opening the door? So opening the door is actually causing a rotation. The hinges, the hinge acts as the axis of rotation, and we apply a force that causes the door to rotate around its axis of rotation. Knowing this, we can establish some factors that impact the ability of a force to cause rotation. First, it depends on the magnitude of the force. This is also true for linear motion. Depends on how big the force is. That makes sense. It also depends on where the force is applied in relation to the axis of rotation or the pivot point. So in this door example, 3 of our forces act at the same distance from the pivot point. They all act at the end of the door, and 1 acts really close to the hinges. And then finally, it also depends on the angle the force is applied at. If hopefully you paused on the previous slide and tested this on the door, on your door, you should have at least been able to see how the distance from the hinge affects things. And you could also probably recreate force 2, pushing along the door. You can also try this with a pencil. And I'm going to encourage you to do this a lot when we're dealing with torque, so you might as well start now. So pinch where the axis of rotation is. So I'm going to say the hinge is about right here. And then just apply a force or like push or pull the pencil wherever the force is applied. So we can start with force 4, which is like really close to the hinge. And I'm just going to pull. And you can see, like, yeah, I'm able to make it rotate. And then we do force 1, which is really far from the hinge, at the farthest possible point, and I can pull that. Okay, that rotates too. Force 3 is a little harder to replicate because, I mean, to see the difference between force 1 and force 3 is hard to replicate. But we can also look at force 2, and that is pushing along the pencil or the door, and you can see that's not going to cause any rotation. So torque tells us how effective a force is at causing an object to rotate. And it's given by the symbol tau, which is like kind of a little t. And we have an example here of a wrench where the pivot is at the end here. And then the force in this example acts near the other end of the wrench, and it is applied at this angle from the radial line, which is just the line from the pivot point to where the force acts. So in general, torque is given by the equation R being the distance from the pivot times the force times the sine of the angle between the force and the radial line. So for this wrench, the radial line is the line from the pivot point to the point where the force is applied, and the force is applied at this angle phi. And the only part of the force that contributes to the torque is the part that is perpendicular to the radial line. So in this example, our force is applied at this angle. The parallel component does not contribute to the torque. So that was just like, instead of pushing along, we're pulling, it's not going to rotate it. But the perpendicular is going to cause rotation. And so that the perpendicular component of the force here is sine of phi. And an angle of 90 degrees between the radial line and the force applies the greatest torque. So if the force was just this perpendicular component instead of this angled one, this would give us the most amount of torque, and then this would give us the least because there would be no torque in that direction. And torque is 0 if the distance is 0. So if the force is applied to the axis of rotation or the pivot, there's no torque from that force. It's 0 if there is no force. That makes sense. And then it's also 0 if the force acts along the radial axis. So, you know, along either pushing along the radial axis or pulling along the radial axis. We already said that's not going to cause torque, but what that really means is 0 torque. And if you forget, you can also check by plugging in an angle of 0 or 180 degrees. So an angle of, either of those are along the radial line, and the sine of those is 0. So let's go back to this now. And again, we're assuming all of these forces have the same magnitude, which it looks like they do. So the only things changing are the distance from the axis of rotation and the angle. So F4 is applied closest to the axis of rotation, closest to the hinge. And that means it won't supply as much torque as force 1, which is at the same angle, 90 degrees, but it's much farther from the hinge. And force 2, again, acts along the radial line, so it does not apply or provide any torque. And that would be true if it pointed in the opposite direction also. And then force 3 acts at an angle from the radial line that is less than 90 degrees because force 1 would be 90 degrees. So it isn't going to apply as much torque as force 1 does. Even though the distance is the same and the magnitude of the force is the same, the magnitude of the force in the perpendicular direction is smaller. So in general, the definition of torque is R times F times sine of the angle between them. But in a description of a problem, you aren't always given the angle between the force and the radial line. Sometimes you're given a different angle. And you can figure out what the angle is between the force and the radial line, but you can also save yourself time by just finding the perpendicular component of either the distance, so R, or the force. So this one, here is the perpendicular component of the force. And then here we also have the perpendicular, I lost my words, perpendicular component of the distance. We're going to do an example that kind of just highlights that a little bit. So Lewis uses a 20 centimeter long wrench to tighten a nut, turning it clockwise. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls straight down on the end with a force of 100 newtons. How much torque does he exert? Okay. So we also have a diagram showing these, but I think I'm just going to draw the lines as vectors, I guess. So let's put, first we have, here's our radial line, and then maybe I'll do force in a different color, and then the force is acting straight down. Okay, and we know that this angle is 30 degrees. So one thing we can do is find the perpendicular component of the radius, because 30 degrees is not the angle between the radius and the force. So we can't just use RF sine of theta. Instead, we can get the perpendicular component of the radius here, which is the radius times cosine of 30 degrees. That's one option. Another option is radius again, and then the force pointing straight down. Then we could find the perpendicular component of the force instead. So this is also 30 degrees. And that tells us that the perpendicular component of the force is also given by cosine of 30 degrees. So we established that the torque is either equal to the perpendicular component of the radius times the force, or the radius times the perpendicular component of the force. In this case, the perpendicular components are both times cosine of 30 degrees. So we can actually just say RF cosine of 30 degrees. And we have a radius of 20 centimeters, which is 0.2 meters, and a force of 100 newtons, cosine of 30 degrees. And this gives us a torque of 17 Newton meters. I'm sorry, before this I didn't say that the units of torque are Newton meters. And that's because it's force times distance. So, but this is showing you where that example I was touching on, where the problem is not always going to give you the angle between the force and the radial line, but it might give you a useful angle still. And so it's totally fine to not figure out the angle between the force and radial line, but instead just use the information you're given to get the perpendicular component of either the force or the radial line. Okay, now torque is also a vector, and torque is the cross product of that radius or distance from the pivot point times the force, or with the force, I guess. And since it's a vector, we should be able to identify the direction of the vector, and this is where we use right-hand rule again. Said in the previous lecture, there's lots of right-hand rules in physics. Here's another one. It's different than the previous one. So make sure you use your right hand. And this is a right-hand rule for a cross product in general. So other times when you're dealing with cross products, it will work the same. So you point your fingers in the direction of the radius or the radial line, and then you curl your fingers in the direction of the force, and your thumb again points in the direction of the torque. So fingers in the direction of the radius, curl. Oh, sorry, I cut off. Fingers in the direction of the radius, curl in the direction of the force, and then your thumb is pointing in the direction of the torque. And I recommend using this diagram if you're having trouble with that as a way to remember. But just remember, use your right hand, not your left. Your left is going to give you the wrong thing. It'll give you the opposite of what it is. So that's all for now. We're going to be spending lots more time with torque coming up, but I want to give you plenty of time to get a little more familiar with it before I pile in more stuff.